Hi, my name is Sabu Francis. I'm an architect by training, by passion, by profession. I'm also a software developer, and I wrote this design software a long time back, and I've been continuously improving it and working on it and using it. I used it in all my practice, and lately I've been promoting this software. It's a free software amongst other architects. In this particular talk, I will be explaining an important concept inside TAD, which is based on something known as object oriented programming. Now, I know that I'm talking to architects here and people who are not programmers, but bear with me, I'm also an architect, and a lot of things which I say is actually from an architect's point of view. I told you I'm very passionate about being an architect. So just bear with me, you will understand this. In this particular talk has two parts. In this part, I will explain the conceptual need for such an approach. And in the second part, I'll give you a hands-on demonstration on how you can use this and how you should use this when you model inside TAD. And we will end up preparing a sample file, and then you can download that file and check for yourself whether, if you follow the same steps, whether you got the same results. So here is a very practical way of understanding the problem statement this handles, and it is to do with the amount of data which an architect really deals with. So let's say that you took a notepad and then you went around your house. Now I am during this pandemic times, we are all stuck in our house, so I'm also at my house. And if you were to go with your notepad and then you went around saying, okay, what all architectural elements are there? So I say, okay, flooring, okay, that's made of ceramic tiles. And then I'll say, okay, I have some shelves over here. I have shelves there. And what is that made of? Okay, that's made of plywood and laminate on it. And then there is the door over there, and then you find that there are curtains there, so you write curtains. I mean, the list keeps going on. What's the material used on the wall? What was painted on the wall? What type of construction happened there? What is the size of the beam? I mean, those are geometrical properties, but I'm talking about additional to the geometrical properties. So what was the screed layer beneath the floor? What was that material made of? What is this glass top made of? And it's not just about visual properties. You would even want, for example, I may want to know for whatever reason, who was the supplier of this particular glass. So I write that down. Then I find what is the weight of this glass. Then is it toughened glass? And what if it breaks? Will it hurt somebody? I mean, it just goes on and on and on, really. I mean, then that's just one room, and then you go to the other room, and then again you start noting down what all characteristics are there. So now architects are pretty familiar with this situation, right? We deal with humongous amount of information. In fact, I wonder whether the computer guys really know what is big data. You know, when I go to computer conferences and they talk something about big data and how it is to be managed, I say, you come here. I'll tell you what big data is. As an architect, I'll tell you what big data is. And I'm pretty sure some of the architects here will be smiling at this, because seriously, even a small apartment it can blow any hard disk if you really look at it. It's not just the physical properties of this particular spaces which are there, what I just explained, but it also receives a lot of additional information. I had been to Thailand sometime, I had been to Russia, and those Russian dolls are there on that shelf over there, and some other curios are there. And then as time passes, there are conversations which happened here inside these rooms here. My children are playing around, and in one sense, all that information, architecture, like a silent obedient servant, has absorbed that and kept it over there. You know, it may sound like a metaphor, but it's probably more than a metaphor. If you I'm sure a lot of you have had this experience. You visit your old college, and just the sight of all that familiar places which you are visiting after now 20 years, and you remember suddenly that conversation which you had, or that kind of milieu of people over there, and your friends over there, and somebody sitting with a guitar and playing somewhere in one corner, they all come back. So that means that particular piece of architecture is driving a lot of information. It's handling a lot of information. It gives you a lot of triggers for enriching your experience and value in architecture. I think I may be overstating the case. I'm sure all architects know this, and I may be preaching to the choir, but I thought I'll just dramatize it a little bit. Now, coming back to TAD. Now, what is TAD meant for? TAD is meant for, the basic mission of TAD is not just to explain the what of the building which you see, which you finally design, but it also need to explain the what of the process as you led to the building. Now, people get confused sometimes, when I tell this, and they're wondering, what is the difference? Why should the what of the building be different from the what of the process of coming to the arriving at that design? Actually, all of you know this, and you may not be able to verbalize it, so I'll verbalize it for you. When we start a design, we are actually not knowing what that design eventually should be, right? I mean, we 1,000 different ideas come into our mind, and we are making bubble diagrams, and then we are figuring out all kinds of if and then, if this happens, then that happens. If I put this window here, then what will happen? And put that door there, then how will people move? And then you will realize that at that various stages of developing the design, also there is a lot of information which we process, right? Like you will work out a bubble diagram, say what would be the area of this living room with respect to that bedroom over there, or the kitchen over there. Oh, maybe I should not put the bedroom here, maybe I should put it here, or maybe it should put there. And that's how finally the design eventually bubbles up, right? And then you have the final design. So when you start talking about the properties of your building, after all that work is over, I mean, that's nice that at least at some point before the building got made, that building has been described. So that is where BIM comes in, building information modeling. Now, a lot of civil engineers and people on the construction, they're very happy with building information modeling, because in one model, all the construction details and all such information which I alluded to some time back, they all get captured inside that BIM. But what BIM does not do is, what are the information requirements before it became a building, before when it was just bubble diagram, what all information was there. So TAD actually covers the whole lot. It starts from very early stages of design. It looks pretty crude actually when you start with TAD, and that is intentional. It is meant for main architects. They don't have much time, so you can just quickly put together even a bubble diagram and then start talking about all these properties of that. You'll say, okay, here is one square. For the timing, let's assume that that's a square. We can change the shape of it later, but it needs properties for us to assess, and this needs to be deposited into a computer system. Why so? So that we can actually do very intelligent what if analysis. What if this living room is made of marble? What would be the cost? Now, you have not yet finalized that entire design, but you may still want to ask such a question. Now, it may sound a little absurd. I gave an example of one apartment, but that maybe on the back of your envelope, and some really talented and experienced architects can really do it without even hesitating. But I'm talking about a whole gamut of projects which may come, you may be doing, right? It may not be this that you will always be doing just that one apartment, right? That one apartment itself has got a lot of complexity, as I just told. But you would also be doing, say there are 300 apartments, right? I mean, you got a pretty large housing complex which you have to do, and there are 300 different type of apartments, and you're the main architect, and now you have to flesh out some basic idea about how that particular design will evolve. And you would want to know pretty quickly, maybe in that situation, that you what if the living rooms were made of ceramic tiles, or what if they were made of granite, the flooring that is, and what if the flooring was made of marble, right? So you cannot sit down and say that I will only do, or TAD is only meant for very small projects. In fact, TAD becomes much more enjoyable when the projects are really large and complex, which is the opposite of what normally happens in software. Other guys, they will say, tiny little demo of something or the other, beautiful it looks and all, but the moment it becomes really realistic, it becomes so difficult to load that file, so difficult to work on it and all that. Anyway, this is not a kind of a spiel about my software. So how do I represent all those properties over there? Now, in 1989, when I initially started with this and I started working out the very first version, frankly did not have this particular object-oriented programming concepts in it. And I quickly realized that this may end up becoming pretty thankless kind of a way of modeling a building, or rather modeling the process of arriving at a building. And I spent a fair amount of time figuring out what can I do so that the modeling becomes both flexible also and accurate also, if you so want it to be accurate, and also that it can receive a huge amount of such properties. What is the flooring, what is the wall, what is various properties which we have in buildings. That is why I'm one of the first guys in the world to talk about what is now known as BIM concept, information concepts inside building. So when I looked around, I realized that this is not something which we can ignore. I can't say that, okay, you know what, you just keep putting stuff into your model, like in 3ds Max or in SketchUp, and then you go to each particular model and then start giving the properties of it. I mean, that's going to be crazy. I mean, the amount of stuff which I'll have to go and deal with that is going to be crazy. So what all options are there for doing that? Oh, you can select some things together and then give properties. Yeah, it can help a little bit here and there. But what I came up with is actually the most efficient system, which is to borrow concepts from object-oriented programming and then use those concepts and brought it into TAD. And in my second part of this talk, I will actually show whatever I'm talking about, and then you'll find that it is seriously efficient. In fact, it is so efficient that in TAD, you can talk about really large buildings, literally in kilobytes. And that's why TAD nowadays, because of the internet, is coming up with a huge amount of power, which is you will probably not get in any other software. So what is object-oriented programming, and why did the software guys adopt it? So software guys also adopted it for the same reason which I just told. Whenever you have to handle a huge amount of data, okay, that is one strong reason for adopting object-oriented concepts. The second reason is when you see certain commonalities in that data, certain patterns, but those patterns can change from one project to the next project. So you cannot hard code that particular pattern. For example, some of the design software will have nice, beautiful GUI, which will say, okay, tell me the brick which is used, tell me the flooring which is used. Now that also can end up becoming pretty rigid, because you are dependent on that software guys to give you those slots where you have to go and fill in, right? That won't work. Anyway, so I think I built up the case for handling object-oriented data, but you do not know what object-oriented really means. So let me introduce a bit of biography of the person who discovered this way of handling data. His name is Alan Kay, and he was actually, when he was a child, he was literally one of those child prodigies. He started reading at age 3. He started reading a lot of books, and I think somewhere I read, and I hope I'm not misquoting, that by the time he went to school, he had read so much, he realized that the teachers are not telling him all the things. I mean, he was quite a brilliant guy. He ended up with 2 bachelor's degrees, one in mathematics Okay, and one in molecular biology. I mean, that was quite a serendipitous thing, and probably my hypothesis, I don't think it is documented anywhere. My hypothesis is that the fact that he knew about biology influenced what he came up with, this concept of object oriented programming. So this object oriented programming can be very sharply given to this particular person, because he was the first person to really explain it very well. There were some precursors to that, and he does acknowledge a few other developments prior to him. But honestly, the whole world of computing, they regard Alan Kay as the first person to talk about object-oriented programming, and he developed a computer language called Smalltalk, which is also an AI language, by the way, and that language has this object-oriented capabilities. So what was this object orientation, and what does it do? So now let me give you a little bit of background of biology. In biology also, they have this huge big data problem of trying to understand properties of plants and animals. So let's take animals, and let's say that I have a dog called Tommy, and I start describing, just the way I went with a notebook and I started describing my house. So now I'm describing Tommy, and I say Tommy is of such and such breed, and then he's brown in color, and he's got this kind of bushy tail and whatnot and all that. Now I encounter another dog, and again I start all over again, and then I find that there are certain things which are common between them. What is that? That both of them actually have the vertebral bone and a skull, right? They are all vertebrates. So you say Tommy has got a vertebral column, then that other dog, let's call that dog as Shadow. So Shadow has got a vertebral column. Now then you step back and say, this way of trying to understand plants and animals and classify them is not going anywhere. You will end up, I mean, there are millions of species of birds and plants and animals and everything, right? So you can't keep doing this with each and every encounter of each and every specific dog. Now both these dogs belong to the class called dogs, right? And yet you ended up describing each one separately. That will end up being consuming a whole lot of data. So there was this gentleman, I think his name is Linnaeus, I think that's why he's called Linnaeus classification system, and he came up with this tree structured classification system. And you know what he said? He said that Tommy and Shadow are actually instances or examples of a class called dogs. Now dogs is a subclass of another class called, maybe I think it's called canines. Okay, now, and in canines, it's not just dogs, there are other canines which will come into that particular class. But then canines are a subclass of another class called mammals. And what is the properties of mammals? So mammals are those animals whose females have mammary glands and they have a uterus and they give birth. The child is born inside the body of the female. And comes out through a birthing canal, and then it comes to the world. So those are mammals. And then you realize that mammals are actually a subclass of vertebrates, and so on and so forth. I mean, this is just an example. I'm not trying to be a biologist here. But now what happens is that instead of sitting down and going to Tommy and say, Tommy has got a vertebrate, Shadow has got a vertebra, and all that, what you now do is, you have given properties right at that point, right? At the top point where you said that there is a class called vertebrates. And what is the nature of that vertebrate class? That it has got vertebra, and it's got, so that the bone structure inside the body which holds up the body. And under vertebrates, there are various different types of classes of animals. So there are fishes, they also have a backbone and a skull, very weak one, but they are there. Birds, they also have that. And then mammals. And then you start realizing that when it came to the next level of classes, you don't have to now specify that it has got a vertebral column and all that, right? Because You already told that at the vertebrate when you talked about vertebrates, right? So that reduce the amount of data entry you have to do at the next level. And then when you came to mammals, you don't have to say later on that, dogs have got mammary glands, the female of the dog, and they have a uterus, and they give birth. No, because at the class itself, you're given those properties, right? So, and by the way, humans are also part of human as a species, that is human being as a species, is actually a subclass of mammals, right? So are bovines, that is cows and buffaloes and bulls and all that, right? So they're also part of mammals. So when you come to cows and all, you don't have to now tell that there are mammary glands and all. Why? Because it already knows that it is from that class. So in short, when you arrange data in such a way that the common set of data which belongs to a particular class is a kind of a collection of an abstract set of concepts. It's like a stereotype, if you want to call it, which is a very poor analogy term according to me. But it is a pattern which you are pretty consistent. You say that, there would be this particular class of animals, and this class of animals have got this kind of properties. Then at the fag end of all that, right at the end of it, you will now talk about examples of that class, which in computer lingo it is called instance of that class. So my name is Sabu Francis. I am an instance, that is an example of the class called human being. And you who are listening to this, you would also be an instance of the class human beings, right? And there will be some shared properties which I have and which you have. Like both of us will have a head, and we'll have two eyes and nose, and there'll be hair. I've lost most of my hair, and all that, whatever. Now you may be a female, so you'll have different set of properties, little bit here and like that, right? But still you're part of that human species. How does it all translate into TAD, and how did I use these object-oriented programming concepts? So in TAD, we have, just like in that lineage classification system, you can actually form a class tree, right? Just like what I just explained about the classification system. That class tree which you put in TAD, you would sit down and say, okay, you know what? I have two kinds of apartments. Apartment A and apartment B. So under project, I will say apartment A, probably 3-bedroom, higher end specification type of properties and all that, and class B, like apartment type B. So apartment type A will have certain types of properties. Apartment type B are probably smaller, and they'll have a different set of specification. Why do we think like that? Because we naturally think in these tree structures. Even as an architect, we'll say, okay, that apartment A has got all these kind of properties, so why should I lump it along with apartment B? Apartment B has a different set of properties. So right there, what you do under project, you'll say apartment A and apartment B. You'll see that in the second part of this. And then you say that each flat inside that, in India we call it flat, it's called an apartment. Okay, a flat or an apartment is one and the same. So you say that maybe there are multiple floors, maybe there are say 4 floors in each of these blocks. So I will say floor 1, floor 2, floor 3, floor 4 are the classes in this project, and that is apartment A, and in under apartment B also floor 1, floor 2, floor 3, floor 4. Now what happens? Why did I do that? Because again, there are certain common properties. For example, if I say floor 1, you can say that all the spaces in that floor 1 would be at the same level. I mean, more or less. We'll come to the differences later, don't worry about that. And the height to which they are extruded, they will also be the same. So because of that, I can divide it as floor 1, floor 2, floor 3, floor 4. Not just because of that, you can also do it based on the specifications of material and all that. Now you have a class tree going on inside your TAD model, and now you can start pouring various properties into that. And the moment you have all those class properties and the thing, I mean, you can do it at your own pace and in your non-linearly. It's not necessary that you have to do step by step. As you keep working on it, you can decide what should be the class tree, and you can of course change around and delete a class and add the class or rename it, and all that can go on, not a problem at all. Now what happens is, where are the instances? So you say, okay, there are various architectural elements, and in TAD we use a term called object. Now object is not really a complete apartment, but the constituents of that apartment would be the rooms inside that apartment, or the various other building elements which is there, doorways, all the openings. In TAD has got a nice preference towards spaces, which I'll explain separately, but if you want to put in built matter over there, be my guest, no issues, you can put that also. So you can talk about both spaces as well as the built matter inside your apartment, and then go around and make them the instances of this class tree which you have created. Now what happens is that, let's say that all flat 1 flooring is made of granite, but flat 2 flooring is made of marble. And that's when it becomes really efficient, because instead of going to each space in flat 1 and say this has got granite, that has got granite, that has got granite, you can set that property at the class level, and you say this class, the property, flooring property is granite, and similarly on the other class you can go and say the property of that class is marble, flooring property, that is. And what happens, what TAD does, that it immediately starts pulling that property. That process is known as inheritance in object-oriented programming. And inheritance sometimes confuses people who are not programmers. Basically, inheritance just means that whatever properties you give at the class level, it goes down and goes into that particular object level or the instance level, at that example level. So when I said that vertebrates have got a property called vertebral column, that went down the class tree, it went into mammals, and from mammals to human beings, and therefore that particular human being, that is Sabu Francis, he has got a vertebral column. Okay, now let's make a joke about this. Let's say there is a coward, and when that coward is there, and I'm just making an arbitrary joke, and we say he's spineless. Okay, so there's a little exception there. Suppose you want to metaphorically say that that person is also the human being here, but he's actually spineless, suppose. Okay, I'm just stretching an example here, pardon me, I just thought of it. And now you want to give, though he's also a human being, right, but he's spineless. So now you have to tell somehow the system that that particular human is spineless. How do you do that? Okay, forget the joke. Let's put it in terms of the actual example which I gave you. Remember, we said that flat 1, all the spaces in flat 1 will have granite as a floor. But then you say, you know what, all the rooms do have granite, but I think that one room needs to have ceramic tiles and not granite as the floor. So now how do you make an exception? So what happens in TAD, and that happens even in object-oriented programming, is that at the instance level also you can change the property and say that this particular instance, the property of floor has been changed and it went from granite into ceramic tiles. In short, what happens is that if you look at the TAD interface also, on the left hand side you will see something called classes and objects. And then there's this major area where you actually see the models of all the in plan form. Okay, you'll see that of all the architectural elements. And as you navigate through the model, you will find that the properties given at the class goes into that object, and then actually that object gets enriched with that whatever property you had created. So this is basically the sum and substance of what you mean by object-oriented programming concepts. I'm not asking you to do programming here, not directly anyway, at least. The reason for doing this is that you are now in a position to deposit a lot of information as the design goes along. Okay, remember that in TAD you don't have to really be so sure about what is the shape of the living room, for example. Now this particular living room where I'm sitting, I modified it. It's like an open kitchen and all here in my house. So there is no hard and fast that it has to be a rectangle. In TAD, some people think, oh, it makes only rectangles. No, it doesn't. It's just a placeholder to begin with, just like a bubble diagram. And then as you become more and more convinced about what you really should do, at that time you can go around changing that particular shape based on whatever you really need. Just like how I set flooring as granite and all, you can even set some of the geometrical properties. The height and the level can be set through the same mechanism. So you can actually start designing a whole set of spaces for a particular floor and keep it at a particular level and extrude it to a particular height, that is using this mechanism. And later on you say, no, you know what, this needs to go to another level, not here. So you can actually put a whole thing up or down or wherever you want with one little change in your class properties. That's it. So that's why working with TAD is really very efficient. Suppose you have 300 apartments and you realize that the headroom for the staircase, there's some issue. So you need to actually shift up the entire floor by just half a meter or so. And you can do that in TAD. And you are sure that everywhere it is affected, the whole thing gets lifted up because you tweak the right property at the class level. So all this I will show you when I will come to the second part of this lecture on object-oriented concepts in TAD. I hope you can download TAD and start using it. Lots of people all over the world, they are using TAD, and I hope you also would use TAD. And I hope all of you remain safe, and let's really come out as better human beings after this pandemic. TAD is available at www.teamtad, TEAM as in football team, teamtad.com. You will see a subtitle here when this video is released. And it's free. You download it, use it, design it, and design your projects, and leave behind really cogent information for the future. And for yourself and for your staff who will come into your office later on, and they want to see what happened in that earlier housing project. What was the percentage the floor area which used marble, and what is the percentage floor area which used granite? I mean, that could be a statistic which you never thought of during that time, but later on it became important. How do you plumb back that information really fast? And that's why you should use TAD. Thank you so much. I'll see you in the second part of this video.